Thanks so much for the invitation. Hello, everyone. Thanks for being here. I'm excited to share this perspective on inner interpretability, specifically from computational complexity, and then some ideas for its integration with experimental efforts. So we begin with the basic fact that modern AI can be architecturally transparent and yet mechanistically opaque. Okay, so this gives rise to the field of post hoc interpretability that tries to explain how machine learning models work after training, right? With a role, like various roles in science and society. And so the plan for today is to look at inner interpretability in the broader context of the intersection of AI and the cognitive and brain sciences, where I have some experience, and to bring a complexity-theoretic perspective to bear formally on this problem. I'll walk you through some results about circuit discovery and where this is headed, and then I'll zoom out to consider the place of this kind of work and how it can be integrated in complexity-theoretic experimental efforts. Finally, I'll just wrap up with the main takeaways. So let's start at the beginning. Inner interpretability, sometimes people call it mechanistic interpretability, although mechanistic interpretability is strictly a subfield of inner interpretability. This is the emerging field that attempts to understand trained neural networks mechanistically. And an example of inner interpretability work is circuit discovery, which you see on the right-hand side, which I'm going to use as a concrete running example, and it will be the subject of the results I'm going to be presenting. And this is the family of problems that broadly takes a trained neural network as an input and is supposed to give us back a circuit with certain properties that are useful in a sense that we will make more precise later. So many proposed applications of AI hinge on the feasibility of this kind of inner interpretability. So it makes sense to try to understand the problems and the possible solutions, right? So in AI and the cognitive and brain sciences, people are conceptualizing this kind of work as useful for building psychological and linguistic theories or neurocognitive models. In machine learning and engineering, for performance improvement, user explanation, and even to extract domain insights where the systems outperform humans, right? Even in philosophy, this is the whole AI plus interpretability toolbox is conceptualized as a possibly novel epistemic perspective, like a new way to create knowledge. And in law and society, this has roles in safety, environment, and even regulation and compliance. But the scientific problem of interpreting complex systems mechanistically is much older. And the first thing we will do in a moment is to put the problem of AI interpretability in the context of pre-existing problems in cognitive neuroscience. And to do that, I'll just quickly tell you about two of our papers where we use this shared context in both directions. So inner interpretability for cognitive neuroscience and cognitive neuroscience for inner interpretability. And so in this first paper, we conceptualize the role of interpretability in cognitive neuroscience, where we have an initial state where we have a target organism that we want to explain. We have a trained neural network in the domain of interest, and we have some mechanistic hypothesis of how the system works. And we have a goal state, which is a mapping between a concrete mechanism and the brain, supported empirically by a neural network that has been interpreted mechanistically. Okay? And so the methodology to get there is you can conceptualize it in two paths. I'm not going to go into detail, but like on the left-hand side, you have a brain to mechanism pathway where you try to map the brain to a DNN using bottom-up interpretability to find components of the network that are good at predicting brain activity. And these DNN components can then be interpreted, right? On the right-hand side, you have a mechanism to brain pathway where you try to map a mechanism to a DNN using top-down interpretability. You try to map hypotheses about how the DNN works, and these components are then used to predict brain activity. And these two pathways have different kinds of biases, so they might give us different, possibly complementary mechanisms, right? So the results are then compared and the pathways are iterated, and interpretability has a role to play in various parts of these pathways, right? So in this other paper, we go in the other direction and use current and old ideas in cognitive neuroscience to better conceptualize the problems of interpretability in AI. So when studying a complex system, we can distinguish levels of analysis to explain its behavior. This is a very old framework pre-existing in the cognitive sciences. It's Mars levels of analysis. And so, for example, we have this level, which has been dropped, and we brought it back, which is the level of primitive representations and operations available to the system to compose algorithms that solve certain computational problems, right? And these very general levels are only specialized when it comes to the implementation of this framework, right? Biological or artificial. And so this makes the lessons from cognitive neuroscience learned over many decades to be useful to modern AI interpretability. So for example, the role of abstraction or coarse graining at the level of implementation, this is going to be the same conceptually. The constraints between these levels and the complementary relation between top-down and bottom-up approaches. So this is all to say that interpretability, even when restricted to artificial neural networks, has a role in a much larger context than machine learning and AI. And this has an impact all the way to how we understand formal interpretability queries, the topic of what comes next. And so the objects of interpretability, the outputs of our interpretability methods, and their properties are going to be used as evidence to support claims about systems other than the AI systems, right? In this case, like humans or other model organisms. So how does this work? It's useful to look at the folklore on interpretability, by which I mean like common, often intuitive knowledge that is not typically questioned and sometimes underlies assumptions behind the research programs at the intersection of the cognitive sciences and AI. So we would like to study humans with all possible invasive and non-invasive tools, and this is our target organism, right? And we settle for natural model organisms that display interesting behaviors and allow for more kinds of experimentation, right? That's not possible in humans. And we can now use artificial model organisms that sometimes display ecologically relevant behaviors. And so we have a sequence of black boxes to semi-transparent boxes to fully transparent boxes that can deal with ecological domains and display rich behaviors to various degrees, right? And so the question is, what are we gaining with these surrogate models, right? And so let's look at some candidate dimensions across these organisms. One is ecology. This is the sort of the environment and the behaviors that you're interested in, right? The other one is mappability, which refers to the possibility of constructing full maps of where each component of the system is located, and to provide adequate descriptions that are useful for experimentation, right? So in neuroscience, an example would be a connectome, right? Then observability is the possibility of measuring internal activity anywhere on this map and external behavior. And perturbability is the possibility of conducting arbitrary interventions on inputs and internal components and their activity. And so if you look at how the organisms score on these dimensions, right, you see that the target organism has the right ecology, because of course that's the target organism, but it's very poor in the others, right? It's very hard to do all the other things. If you sacrifice a little bit of the ecology by going to natural model organisms, you gain a little bit for mappability, observability, and perturbability with current technology, right? But if you go to artificial model organisms, you sacrifice a lot of the ecology, although, of course, this is getting better and underlies a lot of the popularity of neural networks, but you gain like full scores on everything else, right? Artificial neural networks are completely mapped. You can observe activity anywhere at any time, at any resolution you like, and you can perform arbitrary perturbations, right? And so the question is, okay, what do we get from this? And so how do these dimensions relate to what we care about, namely description, explanation, prediction, and control? Does one entail the other, right? Does transparency entail interpretability? And so the folklore, at least in the cognitive and brain sciences, for a long time has been, and I think to a large extent still, is that mappability, observability, and perturbability are the main obstacles to scientific progress. So neural networks are sometimes described as fully specified computational models of cognition or the brain, right? But here we want to go a bit further and want to ask, does transparency really entail the other one, right? And for this audience, I'm kind of, preaching to the choir. But to explore this question and sort of warm up a little bit, we can take a look at a circuit finding problem in neuroscience, right? Before going into circuit discovery in AI. And so this is the problem of finding a circuit that behaves like the network for some specific inputs of interest, right? Like the network, I mean the brain. Right? So interpretability in AI inherits to a great extent this notion from neuroscience. So we can quickly take a look at what this notion is, right? It's a very old notion. The canonical strategy in neuroscience is often described as follows. Describe the behavior we seek to explain in the system, then find the circuits involved. This is what we were talking about today. And then go on to figure out what drives each unit, how signals are transformed, and take further steps to derive useful understanding. And so this is based on the scientific strategy of sort of decomposition and localization. And so we worked a little bit on just scratched the surface of analyzing this problem in general spiking networks. And we model this problem in idealized conditions where you have a full connectome, full observability, full perturbability, and perfect measurement, which, if you compare to the real world situation, this is a lot better. We show that even in these ideal conditions, this problem is very hard and also hard to approximate in terms of the size of the circuit. This means that any procedure to solve this problem in this setting would make mistakes or take an infeasible amount of time, right? Which is very much like normal neuroscience. But one thing that I want to stress here is that the circuit finding part is a prerequisite for the other miraculous part that comes later, right? And so the thing that this cartoon is trying to show, there's a step that is sort of miraculous that this person is trying to specify here. And this would be step 3 and 4 in the circuit cracking problem, right? But what we're proving here is that this basic step of even finding the circuits is very hard already, right? In this general setting, right? But now, of course, I mean, this is only scratching the surface. So you can say general spiking networks can be rich and complex in recurrence and lack constraints on their structure, etc. So what about feed-forward AI architectures like multi-layer perceptrons, let's say, right? So we'll take a look at that in a moment. But first, I want to motivate the complexity perspective specifically. Okay, so let's look at a complexity-theoretic perspective on everything that we have been talking about. So very quickly here, AI interpretability is science has certain scientific requirements for inner interpretability, right? For inference, as I showed in the papers I described, for inference in modeling and alignment. By alignment, I just mean very broadly like correspondence between systems, nothing else. And likewise for society in regulation and compliance, we have requirements, right? In, let's say, for safety critical scenarios, right? And both of these share the basic requirement that we need to understand the constraints of this feasibility. We need to understand what kinds of guarantees interpretability can give for reliable scientific inference and for reliable explanation, right? Without this, it's very hard, for example, in science to understand the correspondence between a system that I'm using to model some natural system, right? Okay, so from a complexity theoretic perspective, we want to look at not just what we could do in principle, right? Which is what a lot of people talk about. Oh, interpretability can do this, can do that. Yes, in principle, we can do a lot of things, but we want to look at what is possible in practice, right? So the main issue that comes up is the computational cost of answering questions or taking certain actions on the systems we are interested in, right? So in other words, the resource demands of interpretability queries. A query that we're going to look at is queries around circuit discovery, right? Specifically finding circuits with specific useful properties. So in the field, this is recognized. This is a recognized issue at a practical level, right? Just to mention one, in this paper on circuit discovery, they say ensuring that a circuit is entirely complete, containing all relevant model nodes and edges is challenging, and no definitive method of verifying this has emerged. The most notable existing method is seldom used due to computational cost. So this is saying we don't have guarantees of correctness given the requirements of the query, and no method with such requirements has been discovered despite efforts by a bunch of very capable independent groups. And our current best approaches have impractical resource demands, right? So this is a classic scenario even beyond interpretability, and the usual response from complexity theory, from a complexity theory standpoint, is to attack the problem from the other side and try to prove that no such method is possible in the first place, in a certain sense. And so this is a classic cartoon depicting a person reporting to their boss that they didn't succeed in finding an algorithm for a problem the boss cares about, but using complexity theory, they can explain to their boss that this is, in a formal sense, tied to the fact that many other smart people have tried to find algorithms for other important problems and failed. Right? This is a way to provide sort of the strongest evidence we can of such a negative statement. And this is one reason we would want to have a complexity theoretic perspective in our toolbox for interpretability. But crucially, I want to be clear at this point that from the outset that this is a fine approach, but it's not going to be good enough for what we're going to talk about today. Try to understand, try to highlight other less common motivations to complement our empirical interpretability work with a complexity theoretic strategy, okay? So one thing that one might wonder when you think about computational cost of interpretability is, what is the scale of the challenge, right? So here's a thought experiment. I'm going to stress thought experiment as in not a tight formal argument. This is just for you to play around with assumptions in your head, right? And try to get a sense of the scale of this challenge, right? So here you see the size of the input to an interpretability query in number of neurons on the x-axis and time in seconds on the y-axis, okay? And so you have different functions of the input size are plotted there, possible functions of the input size, reflecting the possible time complexity of different interpretability methods, let's say for circuit discovery, right? And here the dots are different model organisms that people study plotted according to their brain size and lifespan. So here you have a worm, fly, a rat, octopus, monkey, and humans, okay? Different model organisms that people do study. And I'm drawing a line crossing the human lifespan because it's important since any model interpretation time must finish before this, right? Actually, a lot before this, but surely before this. And of course, this is being ridiculously lenient, right? And here's current DNN models also in a roughly and conservative way. So any procedure with a scaling law that lies above a point representing an organism cannot be used to understand that organism, right? Because it would take longer than the lifetime of the organism, which is a lenient requirement itself. So it's clear that we would like ideally sublinear procedures, but for sure not exponential or higher ones. And the crucial point here is that some queries cannot have such efficient algorithms unless we make further assumptions, right? So again, I'm going to stress that this graph is potentially misleading, but it's just meant for you to play with these assumptions, right? So if you think that we're overestimating time because compute steps likely take less than a second, of course, then you play around with that and see how the picture comes out. The broader point is always going to be, it's always going to hold, right? And so, okay, that's sort of thought experiment, right? But what do we see empirically in work on heuristics for circuit discovery? Okay, discovered circuits, what we see is that they don't have the ideal properties that we specify, right? So knocking down circuits does not have the intended effect, and they are not minimal. This is what we see in general. So empirically, we do see a picture that is consistent with a breakdown of scalability and consistent with heuristics that we don't understand being deployed to solve computationally hard problems, right? So the summary of the current state of things is that there are concerns about guarantees, about scaling up. We have promising and puzzling results like the ones I just described. And the status is that the theory of all of these issues is comparatively unexplored. And experimental approaches use mostly heuristics with no guarantees, small networks or large basic units, and low complexity domain-specific toy tests, right? So what we need to note here is that the concerns have a natural home in computational complexity, and the way that a lot of the field deals with this sort of sidesteps the complexity barriers, right? The first thing we need is a conceptual framework to anchor formal interpretability queries in some notion of mechanistic understanding, right? So this is very contentious, how to define mechanistic understanding, but we can take a pragmatic attitude towards this, and we can stipulate that useful mechanistic understanding is the capacity to answer certain questions and to take certain actions of interest on the system that we care about, right? So in this type of question-based understanding, we are looking for simple descriptions that allow us to efficiently answer a family of questions in the domain of interest. And the other kind of action-based understanding, we're looking for simple descriptions that allow us to efficiently exert some amount of control on the target system, right? And again, what I want to highlight here is that these requirements themselves, in sort of definitionally for interpretability, have a natural home in computational complexity. The other thing that you might speculate is that circuits as interpretability objects might be good candidates to provide this kind of operational mechanistic understanding, right? And we will see how in a few seconds. So complexity, what for? Well, for practical reasons that we highlighted, right? We want to understand guarantees, why current heuristics fail. We want to understand current empirical results a little better. Theoretically, we want to understand the problem of interpretability itself, right? Which kinds of explanations can be found under certain assumptions, and mathematically understanding mechanistic interpretability in terms of what it can afford for description, explanation, prediction, and control, right? And finally, meta-theoretically, we want to understand how to gain knowledge, both in how to assess frameworks that propose interpretability as a component of some research, right? Like I showed in cognitive and brain science. And also we want to understand how to gain knowledge of interpretability itself, right? Which is going to be the topic of the last part of the talk. So, okay, I think I'm going to leave it there in terms of recap, and just move on to the main part where I will walk you through some results on circuit discovery. So we saw that, for example, the problem of circuit finding in neuroscience, in the very general case that we saw, is intractable, right? One avenue here is to say, okay, let's bring a lot of constraints from what we know about the structure of brains, right? Another avenue is to explore these circuit problems in artificial model organisms, right? In architectures such as feed-forward multi-layer perceptions, right? And we're going to do that now. So I'm going to talk about the results from this ICLEAR paper. This is work from with co-authors Martina Vildas and Todd Wareham. In this work, we aim to formalize a space of circuit queries that one might be interested in for interpretability and to analyze their computational properties and to explore relaxations, parameterizations, approximation schemes, and otherwise variants of these problems. To study the sources of complexity of these problems, what makes them easy, what makes them hard, how might this explain experimental results. And I will walk you through a set of circuits, like kinds of circuits, and their different properties and the complexity of finding each kind of circuit, okay? So here's a circuit that you might be interested in, right? A sufficient circuit, by the way, like terminology and interpretability is a hot mess. And I don't think I think we have contributed to this mess. So apologies for that. As a field, we're going to do better. But for now, I'm going to try to define the concepts as I go. So for us, a sufficient circuit it's a circuit that behaves like the network, right? It's sufficient to reproduce the behavior of the network over a subset of the domain, right? And here, like small circuits are usually thought to be more interpretable, right? And that's why we have to pay attention to their size. We also pay attention to their what's called minimality, right? Minimality broadly says that the circuit doesn't have superfluous components in some sense, right? A subset minimal circuit is one that there's no subset of the circuit that that fulfills the requirement of sufficiency, that is faithful, in this case, faithful to the network, right? It could be minimal in like less stringent ways, right? But that's the basic idea. And so for this problem, don't worry about this is the formal definition, but I'm going to walk you through every step. So here I'm going to show you in the schematic, I'm going to show you an example. This is not a definition, it's just an example. So the whole network is a sort of a trivial sufficient circuit, right? Whole network, of course, is a circuit that is sufficient to reproduce the behavior of the network. Right? And the minimal sufficient circuit I'm stipulating here is the red one, right? Which there's no way you can take things out of the circuit without breaking that faithfulness, right? But here I'm going to show you that there's another sufficient circuit, right? There's also minimal, but it's also it's furthermore minimum, right? Because the size is smaller than the other minimal sufficient circuit. Okay, these are just examples. So the result we get from this is the whole table of results in the paper. Don't worry, you don't have to process it. I'm going to do this so that I'm going to focus your attention to the results and I'm going to walk you through them. So for finding these circuits, the basic problem is NP complete, right? And we see a separation here, which I'm going to talk about later, between the problem of finding circuits that are sufficient for a set of inputs that you care about versus a circuit that is sufficient for all possible inputs. Then what you see there is that finding a minimal sufficient circuit is also NP complete. These problems are hard to approximate as well in a few senses that we investigate. So they're hard to approximate in an additive way, such that you are guaranteed to be a constant away from the optimal size. In a multiplicative sense, like there's no approximation scheme such that if you invest more time, you get better solutions for these general problems. And in a probabilistic sense, like algorithms that are probably correct, but definitely efficient, or probably efficient, but definitely correct. One further step that we take, leveraging the framework of parameterized complexity, is that we want to try to understand okay, this is a hard problem or a set of hard problems. What could be the sources of complexity of these problems, right? One might think, okay, maybe the width of the requested circuit, right? If I keep that small, is it easier to find circuits, right? Well, we investigate a bunch of these parameters, like the most obvious one, like the network width, the network depth, the circuit width, and the circuit depth. And we are able to prove that by themselves, these things are not able to account for the complexity of the problems. They don't become easier by keeping these parameters small, right, by themselves. And also, I mean, this is just an aspect of our proofs. The hardness holds for very shallow networks like 2 layers. So sufficient circuits are sort of considered in isolation, right? They're sort of related to pruning. But what if you're like, your mind works more in the in the context of circuit patching, right? You want to consider circuits that work in the context of other activations for other set of inputs. So, for example, you replace activations of a set of neurons with the activations of some category of inputs, and the rest is populated by some other input, right, from a different set. So you want to guarantee that the response of the network corresponds to the, let's say here, the red activations, right, independent of the other patched components, right? So for this problem, we find a very similar picture, right, which makes sense. I could have presented these two problems reversed for you so that you would see a very general problem followed by a more specific one. Sorry. In that case, we see a very similar pattern of results, which are here. So moving on to the next kind of circuit, necessary circuits are collections of neurons that, when knocked out, are guaranteed to break the behavior of the network, right, and of all possible sufficient circuits in the network. So again, you can think about the size, the coverage, and the minimality of this set. And the minimum necessary circuit is the smallest such set. And you can think of these like, if you want to think about what are these for, you can think about primitive computations that this might help you to infer, shared components between many different sufficient circuits, or universal breaking points, right? Because if you touch these, you're guaranteed to break everything. Okay, this perhaps not surprisingly, I don't know, this is very hard too. What else can I say about these classes? I'm going to leave it there. If you want, you can ask me. Okay, so those problems are very idealized and very hard. So what about like other stuff, like checking certain properties? Like circuit robustness is a problem that's related to redundancy. This is something that comes up in neuroscience a lot, and to some extent in AI, but not so much. So redundancy is in this case relates to how robust is a certain circuit to different kinds of perturbations, right? So one can say that the problem of circuit robustness is related to how many ways you can break a circuit without breaking its behavior, right? So you can think of trying to break this set of orange neurons, right? You want to try to break it by taking 2 neurons at a time, right? And let's say it doesn't break, right? So you can try to break it by taking 3 neurons at a time, right? So being K robust is a property that says this set of neurons, orange neurons, is 3 robust if you can try to break it in 1 way, in 2 ways, and in 3 ways, and it doesn't break, right? That tells you in some way that there's a lot of redundancy in this circuit, right? And interestingly, this sort of relates to, okay, it also relates to, let's say, the notion of an unnecessary circuit, because if you can break a set of neurons, right, in all these ways, right, it doesn't matter. It tells you that this one in the larger context is sort of unnecessary, right, in that very narrow sense. This will also relate to local minimality of the circuit in an interesting way that is also got picked up by Shachaf and others. So verifying that a circuit is K-robust, right? When you're talking about the whole circuit and it's a sufficient circuit, certifies that that circuit is not locally minimal up to that K, right? A circuit can be locally minimal in the sense that, let's say you take one neuron at a time, and any of these neurons is going to break the behavior of the system, right? It's sort of the flip side of this problem, robustness and local minimality. The result that we get for this is it's co-NP complete. It's again sort of hard as the others, but in this case, when you keep the size of this set of neurons that you're interested in assessing their redundancy, let's say, or their robustness, if you keep that parameter small, then the problem becomes fixed parameter tractable, right? It's a technical term, tractable. You can think of tractable. Okay. All right. So again, we saw that a lot of these problems are hard. The natural thing to do is to start relaxing a lot of the requirements, right? Or start exploring variants, right? What can we find that is feasible from the other side, right? And a very drastic relaxation is that is the circuits that can be described as quasi-minimal, right? Quasi-minimal circuits are minimal in a much weaker sense, right? The only requirements is that they must be sufficient and that at least one breaking point of the circuit is known. What about their size? We don't require anything about their size. You can sort of try to control the size heuristically, but strictly we don't require anything, right? And so just to give you a sense of what these circuits are, and in case it's not clear, again, here in the network, you have the whole network is a trivial sufficient circuit. A non-minimal sufficient circuit are these orange ones with this dotted one too, right? And it's non-minimal because I can take this dotted one out and it will be sufficient anyway, right? A minimal sufficient circuit is the orange one without the dotted one, the orange dotted one, right? This is an example I'm stipulating for you to get intuition. It's not a definition. A minimum sufficient circuit is the red one, okay? The sufficient circuits share this red and orange one, and we are saying that's a necessary circuit. If I touch that one, I'm stipulating I'm breaking all the sufficient circuits, right? And a quasi-minimal sufficient circuit, finally, is the non-minimal circuit, right? The dotted one with the orange one, and that neuron, right? That when I touch it, it breaks the behavior of the circuit, right? I can discover, let's say, this is one possibility of what you can discover if you have a method to discover quasi-minimal circuits, right? Again, it's a specific case, an example, so don't generalize it too much. Okay, quasi-minimal circuits can be found efficiently, and you can apply sort of the notion of quasi-minimality to, let's say, sufficient circuit or patching. You can apply to this notion of quasi-minimality to any other kind of circuit that you have a predicate for, right? And this the notion of quasi-minimal sufficient circuit and its properties is perhaps a good mental model for how to understand the circuit discovery heuristics in the literature and the results that they obtain, right? This is the relation is not super strict, but it's something that you can think about. If we look at one way to compute these circuits, we arrive at a procedure that looks a lot like some of the available circuit discovery methods out there. And so the obvious question that you might want to ask yourself is what would one expect of the behavior of such a circuit, right? Is according to the properties that I just stated, is that there are at least some ways of breaking it, giving evidence of relevance and minimality, but there are some ways of perturbing it without change to the input, right? Too, giving evidence of lack of minimality. Empirically, you can have some evidence of faithfulness, but you will also likely find that for some inputs, there is lack of faithfulness, okay? So if you remember what we said about the empirical results that are already out there, they look very much like this, right? So one would say, okay, are we finding some quasi-minimal circuits? And so you might ask yourself, okay, this is a tractable query. How can we find these circuits? I was just checking my time. I'm okay, right? Here's a fast way to do it. So you arrange your network in a sequence, right, where you subtract by some rule. Maybe you're using information about the weights or gradients or whatever. You subtract nodes element by element in this list until you reach a point where the network is disconnected, right? So you are going to have in the middle some interesting middle network with some probably some interesting properties. And so the first item in this list is going to have the property that you care about. Let's say here you're looking for a sufficient circuit, right? And so the first one obviously has it. The last one obviously doesn't have it. And so you break this list in the middle. You basically do binary search now. And then, so you went to the middle and you find that the property holds. So you split that half again and the property doesn't hold. You do that over and over again until you find two networks in this list, one which has the property, the other one which doesn't have the property. And you know, because of the way you arrange the sequence, you know what is the breaking point, right? So that's a way you can find these circuits. That's not a methodological proposal. This is just a very coarse demonstration of how you find them, how you could find them. All right. So let's see what we have total. So we saw sufficient circuit patching, necessary circuit, and circuit robustness. And I didn't talk about other results, but you can check them out in the paper. Overall, what we see is this challenging complexity landscape, at least for these very general formalizations. We see some separations that I didn't talk about between these circuits that are sufficient for a set of inputs versus sufficient for all possible inputs. And here I just want to focus on the fact that, so here, okay, that separation shows that there's something that is NP complete and there's a different, a more general, a more ambitious formalization that is sigma P2 complete, right? That says it's harder, it's even harder. So here I just want to focus on the fact that when you find some problem that is NP complete, you can take it as good news in some sense, right? You can say, okay, it's NP complete, that means that it's not harder than NP complete. And so I can use heuristics that have worked well for NP complete problems on this, right? So in that sense, you can even take it as good news. I talked about this relationship between quasi-minimal circuits and minimal circuits. And we can even find here in this landscape some open problems. So for example, finding an unbounded minimal sufficient circuit, it's a minimal sufficient circuit without requirements on its size, is something that we did not establish its status, right? And so we have minimum sufficient circuits as a very hard problem, and quasi-minimal sufficient circuits is an easy problem. You want to wonder what's in the middle, right? And I talked a little bit about circuits that can be K-robust and its relationship to local minimality, right? What I want to highlight here is that there's this useful intermediate space of open problems that we highlighted as useful. And I just had the super pleasant surprise the past week that I found this paper by Yaron Shachav. And they work on this intermediate space and show some conditions where it's possible to find these circuits efficiently. All right, I think I really recommend reading that paper. With that, I can either move on to, because it's 4:45 already, I can either move on to integration of this complexity theoretic approach and experimental approaches, or let you ask me questions? I don't know what the organizers prefer.
I mean, it would be great to have time to ask some questions, but I don't know if you want to quickly go over some results first. So I think it's a bit up to you as
Okay.
well.
I'll just give you, okay, I'll just jump to this slide. So the basic, I don't see this discussed enough. Like this thing, what are we doing, right? What is it that we have been doing in the whole sort of research program that I showed you results for, right? What is that doing, and how does that integrate with people just doing experiments with heuristics, right? I don't see that discussed enough, either of those two things. So I'm going to try to show you one very simple possibility to integrate these two things. So this strategy involves two paths, a computational path and an algorithmic path, right? The focus is on discovering parameters of interpretability queries that are sources of complexity, like the ones I mentioned before, right? And these are supposedly responsible for making queries hard to solve. And these should be either naturally confined, like empirically you find them that way, or they could be somehow controlled to make interpretability feasible, right? And these parameters can be exploited by the computational path in modeling, in the computational modeling of interpretability queries, examples as I showed before, and their analysis with parameterized complexity theory, again, as I showed before, right? Then the algorithmic path is something that people are more familiar with as the algorithmic design of interpretability heuristics, right? And here I'm not thinking so much of the algorithmic design where you immediately want to find some guarantees, right? I'm thinking about the more intuitive experimental approach where people have some intuitions for why something might work, right? And these are mostly empirical intuitions. So you have in this path the algorithmic design of interpretability heuristics and a parameterized performance testing, right? And the hypotheses for these parameters come from formal observations related to computational problems and the role of the parameters there, and empirical observations, such as, for example, the performance of existing heuristics on certain architectures or domains, right? And this process gives results on each branch of this strategy, give you tractable, intractable formal queries, and accurate or inaccurate performance of empirical heuristics, right? So you'll have there, like, just to not go too long with this, you'll have there theory versus experiment agreement or theory versus experiment disagreement, right? And the idea is to, I can give more details on this, but I don't want to go too long. But the idea is to always ask why, right? If you get a formal query that is tractable and the heuristic is not giving you good performance, or the other way around, you're going to want to ask why, right? And likely your formal problems are, let's say, overgeneralized. They're more general than what you get in practice, and you get a family of heuristics that performs very, very well because they exploit implicitly some structure in the real world problem, right? That your formal problem is not capturing, right? And also the other way around, you want to always question the result you get on the one side and on the other, right? And so this is going to give you feedback for these formal observations that go into hypothesized parameters, right? From the empirical side and from the theoretical side. And a useful, I think, sort of fantasy is to look for gradients in complexity and performance gradients. And I'm putting scare quotes in gradients because obviously this is, I call it a fantasy because in the space of problems, the space of problems can be super jagged and like messy, right? There's no guarantee that these gradients are going to exist for your problem of interest. But if you pay attention and you're lucky, you might find these gradients, and these are very useful both theoretically and empirically. All right, I think I'm going to leave it there. I can go into more detail if people want, but for now, I'm just going to say Thank you. There you have the paper in case you want to check out some details. And I'm happy to take questions if there are any.